Have you ever found yourself squinting at a graph, trying to guess where a limit is? Or maybe you've spent way too long plugging numbers into a table just to get an estimate? Well, if that sounds familiar, you've come to the right place. Today we are ditching all that guesswork. We're going to unlock the power of the limit laws to find exact, perfect answers using algebra.
Right? I mean, eyeballing a graph can get you close, but it's not exact. And filling out tables, it's just tedious. There has to be a better way. And the answer is a huge, resounding yes. We're about to take a giant leap from just estimating to having algebraic certainty. It's going to make finding limits way faster and honestly a lot more satisfying.
Okay, so let's pop open the toolbox. I want you to think of these limit laws as your brand new set of algebraic tools. These are the wrenches, the screwdrivers, the essentials we're going to use to take apart any limit problem piece by piece, figure it out, and put it back together to find the solution.
So first up, we've got the sum and difference laws. And the best part about these, they are just so simple. If you're trying to find the limit of two things being added or subtracted, you can just find their limits one at a time and then add or subtract the results. It works exactly the way you'd want it to work. It just makes sense.
And you know what? The same kind of thinking applies to the product and constant multiple laws. Got a constant multiplying your function? Just pull it right out front of the limit, no problem. Dealing with two functions multiplied together? Find their limits separately, then multiply the answers. It's all about breaking big, complex problems down into smaller, much easier pieces.
Next, we have the quotient law. And again, it's pretty intuitive. The limit of a fraction is just the limit of the numerator divided by the limit of the denominator. But, and this is a huge but, this one comes with a critical warning label. The limit of the bottom cannot be 0. This is a super important point, and it's basically setting the stage for the main puzzle we're about to tackle.
And finally, the power and root laws. These round out our basic toolkit. They basically let us push the limit inside a power or a root. So, with all these laws in our back pocket, we are now ready to handle pretty much any arithmetic we find inside a limit. And that is where the real fun begins.
So why did we just go through all those individual laws? Was it just a bunch of rules to memorize? Absolutely not. Because when you combine all of them, they unlock this incredibly powerful, almost magical shortcut for a ton of different functions. This is our first big win.
And here it is, the direct substitution property. For so many of the functions you see all the time, I'm talking about polynomials, most rational functions, finding the limit as x approaches some number a is as simple as it gets. You literally just plug a into the function. All those laws we just talked about work together behind the scenes to give us this super efficient shortcut.
Let's just pause for a second and appreciate how powerful this is. If you want the limit of, say, x squared plus 3x as x goes to 2, you don't need a graph. You don't need a table of values. You just substitute 2 in for x. It's that easy. This should always be the very first thing you try when you see a limit problem.
But you know it can't always be that easy, right? What happens when our beautiful shortcut hits a wall? What happens when we try to use it and something goes wrong? Specifically, what do we do when that warning label on the quotient law flashes and the limit of the denominator is 0?
You get this, the indeterminate form, 0 over 0. Now let's be crystal clear about this. This is not an answer. It doesn't mean the limit is 0. It doesn't mean the limit doesn't exist. It's a signal. It's the universe of math telling you, whoa, hold on, the answer isn't that obvious. You've got to do a little more work.
The most important thing is to see 0/0 not as a dead end, but as a clue. It's an invitation to solve a puzzle. It's telling us that even though there's a hole in the graph right at that point, the limit, what the function is approaching, probably still exists. We just need to use some clever algebra to find out what it is.
So, how do we solve this puzzle? Well, if the main highway of direct substitution is blocked, we take an algebraic detour. Let's walk through 3 of the most common and clever tricks for dealing with that 0 over 0 form.
First up, good old factoring and canceling. If you get 0 over 0 with a rational function, that's a massive hint that the top and bottom share a common factor. That common factor is the culprit. In this problem, it's x minus 3. Once we factor everything out and cancel that troublemaker, the division by 0 problem vanishes. Now we can use our direct substitution shortcut and we get our answer, 3/7.
Okay, but what if you see a square root in there? That's your signal to pull out a different tool, multiplying by the conjugate. By multiplying the top and bottom by the conjugate of the expression with the root, we're using a neat little trick, the difference of squares, to make that root disappear. When we do that here, poof, an x plus 1 term magically appears on top, which cancels with the bottom, and our 0 over 0 problem is solved. The limit is 1/2.
And our third trick is for those messy-looking complex fractions. You know, fractions inside of other fractions. The strategy here is really just to tidy up. Find a common denominator for the mini fractions, combine them into one, and almost every time you'll uncover a hidden factor that cancels with the main denominator. Here, that cleanup job reveals an x minus 1 term, which lets us cancel and find the limit is -1/4.
Okay, but what happens when the algebra just isn't working? What if you're dealing with a function, maybe one with trig in it, that you can't factor or simplify away? For these really stubborn cases, we have one final, super elegant tool in our kit. This is the squeeze theorem, and the idea is actually pretty simple. Picture this. You've got a function, g of x, and you can't figure out its limit. But what if you can find two other functions that trap it, one that's always above it and one that's always below it? If you can show that both of those outer functions are heading to the exact same point, well, the function in the middle has no choice. It gets squeezed to that very same limit.
And trust me, this isn't just some weird abstract theory. The squeeze theorem is absolutely essential. It's the key that unlocks one of the most famous and important limits in all of calculus, the limit of sine theta over theta as theta goes to 0. Without proving this limit is 1, we couldn't do the derivatives of sine, cosine. It's that big of a deal.
So let's wrap this all up into a simple game plan. Here's your framework. Step 1. Always try direct substitution first. If you get a number, you're done. Awesome. Step 2. If you get that 0, signal, don't panic. It just means it's time to open your algebraic toolkit. Pick the right tool for the job: factoring, conjugates, or simplifying. And for those really tough cases, remember you've got that secret weapon, the squeeze theorem. Ultimately, what we've really learned is that finding limits isn't just about memorizing formulas. It's about building a versatile toolkit. It's about learning to recognize what kind of puzzle you're looking at and knowing exactly which tool to pull out to solve it. So the only real question left is, what puzzle are you going to solve next?